If you've ever used a color picker, you probably noticed that pure white has a value of FFF, while black is 0000000, which seems backwards, right? White often is seen as the absence of color. So why does white have the highest value instead of being at the starting point at 0? On digital screens, white is not what you think. Screens have pixels that each contain red, green, and blue light, but no white light. Yet for some reason, when these red, green, and blue lights are combined, it makes white. Meanwhile, the opposite happens when we mix red, green, and blue in real life. So today we're going to decode what these color values mean and why color works completely differently for computers than it does in real life. First, we need to talk about pixels. As you already know, pixels are the tiny lights inside of our digital screens. Everything from our TVs to phones to computer screens have millions of these pixels. From a close-up look, you'll see that each pixel displays a color that makes up the larger image. But if you take an even closer look, you'll see that actually, a pixel isn't just one light that changes to any color you ask it to. Instead, a pixel is actually 3 separate lights, called subpixels, with one red light, one blue light, and one green light. The lights can change their brightness from all the way off to their brightest level of red, blue, and green. And by adjusting the brightness of each in different combinations, a pixel can produce close to 17 million different colors. When all the subpixels are turned off, their combination produces black. But when each of the subpixels are at their brightest, they produce white. Or at least, that's what we see. Our eyes are filled with cones and rods. There are 3 cones responsible for our ability to see color. The L cone lets us take in long wavelengths, which we know from the electromagnetic spectrum produces red visible light. M cones let us take in medium wavelengths, which we interpret as green, and S cones take in short wavelengths, which we interpret as blue. Our eyes can take in a combination of wavelengths at once, and that's why we see a variety of colors. But when we take in all these wavelengths at once at a roughly balanced level, we see white. This is considered additive color because it creates color by adding wavelengths together. In contrast, the colors we see outside of a digital screen is pigment. Pigment instead absorbs certain wavelengths and reflects others. For instance, when we see the color red in real life when it's being illuminated by white light or the sun, we're interpreting it as red because the blue and green light waves are being absorbed while the red is being reflected back into our eyes. The more pigment we add, the more the light waves get absorbed, and that's why mixing colors together make black. Okay, so that explains why white is at the end of the spectrum when it comes to digital color, but why is its value FFF? It may seem like a random value, but it's not random at all. As you may know from my older videos, anything digital always comes back to binary or ones and zeros, aka the language of computers. Each subpixel can be represented as 1 byte. A byte is 8 bits, and each bit can either only be 1 or 0. But imagine if we had to write every color by the bit like this. This would be a headache. But the nice thing is, we can convert binary, which is also known as base 2, since any number in binary can only be represented by either 0 or 1, to base 10, or the decimal system, which is the number system we understand. If we do some simple math, knowing that each bit can either be one of 2 options, that means there can be 256 intensity levels. You can convert every combination of bits into a decimal by using this equation. Starting from the right, assign each bit a number, starting with 0 and increasing by 1 until you get to the end. Then, calculate 2 to the power of that position number. After you do that for each bit, multiply that value by the bit value itself, add all of those numbers up, and that's your decimal value. So its lowest intensity would be 0, while its highest would be 255. This is why you may also see color represented by its RGB value. White is 255, 255, 255, while 000 is black. Okay, so now we're getting somewhere. We have officially landed on the color picker. I'm sure you noticed that most color pickers include both the RGB value and the hex code. But how does this equal this? So we know the ones and zeros value is in base 2, aka binary, so computers can understand. And the RGB value is in base 10, aka decimal, so we can understand. But to make things even easier for us to read and memorize, the hexadecimal system was created, which is base 16 and has the values of 0 through 9 and A through F. This is how these color codes are calculated. Specifically, they're called hex codes. You've seen hexadecimal in a bunch of other places as well, like the back of your Wi-Fi router. It was created as a shorthand way for humans to read binary. Plus, it's easier to remember than a bunch of numbers. While you can convert decimal to hexadecimal, let me show you how to go from binary to hexadecimal because I think it will make more sense. First, you want to split each byte into 2. And if 8 bits is 1 byte, guess what 4 bits is called? A nibble. Yep. If we do the same math as earlier to convert binary to decimal, we'll see that at minimum, a nibble value can be 0, and at maximum, it can be 15, resulting in 16 different values. The first 10 follow the same rules for base 10. So 0 is 0, 5 is 5, and 9 is 9. Once it hits 10, we switch to letters. So 10 is A, 11 is B, 14 is E, and 15 is F. So why is the hex code for white FFF, FFF? Because FFF, FFF.